So in our previous video, we covered finding an area between two functions when the bounds of integration were rather clear. This video is sort of about, how do we find the bounds of integration if it's not made clear to us? And there are really two common sources for those bounds. The first is finding points of intersection of functions, and the second is finding the x-intercepts. In this video, I'm not really going to talk about the process of finding x-intercepts because we did that in previous videos. In fact, right when we started this chapter, we were concerned with finding the area between a function and the x-axis, and there were times where you had to find these points, and the reality is all you need to do is set the function equal to 0 and find the x-coordinates. We've done that before. I don't think it's going to be a problem. So this video I'm going to go through an example where we actually find the points of intersection. While I'm here, I might as well mention sometimes you'll need to do both of them. I could envision a problem where they might ask you, actually, we may have even done that in a previous video as well. Suppose you had something where this is the function f, and this is the function g, and you wanted to find this area here. You would need the x-intercept of the f function. You would need the intersection of f and g for that bound, and you would need the x-intercept for g as well. So sometimes you're going to need both of those things, whether there's a bottom function or not. So that's sort of our setup. I'm going to go next into the example we have here where we have to find some bounds of integration. So as an example, suppose you were asked to write and evaluate an integral expression to find the area between these two functions, f of x being negative x plus 2 and g of x being 2 plus 2x minus x squared. I think it's worth, if possible, and it really is here, it's worth spending a minute seeing if you can even sketch an idea of what this looks like. The graph of f is negative x plus 2, which means it's up 2. And from there we have a slope of negative 1. So you've, kind of got something that looks like this. And there's our line. It doesn't need to be perfect. For the other one, what do we know about this parabola? Well, we know it has an x-intercept of 2, which is exciting because we just found one of our points of intersection. Further, using the formula x equals negative b over 2a, we can find where the axis of symmetry is. So I plug this in, that's negative 2 over 2 times negative 1, means the axis of symmetry is at 1. So that means your graph is going to sort of be going up to its maximum there, and then curving back down on the other side. And I may not know exactly where this is going to intersect, but we have a sense it's going to be over here somewhere. And so the region that they're talking about is clearly this region in between here. And based on what we've learned in our past videos, we know that finding the area of that region will be as simple as the integral of the top function, which is the 2 plus 2x minus x squared function, minus the bottom function, which is negative x plus 2. The only question is, what are these bounds of integration? Right? And we even noticed before, because we graphed carefully, that left bound is definitely 0. Because the x-coordinate of that point of intersection is 0. The one we need to figure out is, where does this thing end? And the way that we do that, because that point is a point of intersection, is we do that by setting these two functions equal to one another and finding the x-coordinate where that happens. So we'll come back to that integral in just a second. For the moment, we'll step over here and take a look at, when does negative x plus 2 equal 2 plus 2x minus x squared. So, if I subtract the 2 over, if I subtract the 2x over, if I add the x squared over, sort of move everything over all at the same time, I will end up with, let's see here, that's a plus 0 there. We basically got x squared minus 3x, that's terribly ugly, x squared minus 3x equals 0. If I factor this thing, I end up with x times x minus 3 equals 0. So my points of intersection seem to be at 0 and at 3, which is really nice. That actually confirms what we saw over here before. We saw that the left bound was 0. It makes sense with my graph that this would be 3. So now I just need to do the integral between 0 and 3 to find out what that green area is. As always, I'm going to recommend that you pause the video and work through this integral on your own, just to make sure that you've got those basic skills down. So do that now, and then we'll check your answer. Keep in mind, you should always simplify an integral before you actually do that integral. So I'm looking at this as 2 plus 2x minus x squared plus x minus 2. And so we notice that the 2 and the negative 2 are opposites of one another. The 2x and the plus x join forces to become 3x minus x squared. And now this is nice and simple. I can just take the integral of this thing and plug values in. This is going to be 3 halves x squared minus 1/3 x cubed. This whole thing is getting evaluated from 0 to 3. So we plug in the top number. That'll give us 27 over 2 minus 27 over 3 minus. Then we plug in our bottom number. We plug in 0 and get 0 minus 0. Let's see here. We'll want to get a common denominator here. This will be 81 sixths minus 54 sixths. And subtracting those two things gets us, is that 27 sixths? It should be. Yep. And that actually simplifies further. We end up getting 9 halves for that. So assuming I didn't make an arithmetic error there, the area of the region that we just found was 9 halves. And that's actually about all I wanted to say in this video. The short of it is, if you've got a region and it's not obvious what the bounds are, draw a picture and look at what's creating the bound. Hopefully we can go back up and look at my graph here. In this example, the things that were creating both boundaries were intersections of the functions with one another. So if I want to find out what these bounds are, I should set the functions equal to one another as we did over here. Set the functions equal, find out where, I guess that's further down, find out the x coordinates where those intersections happen, and those things will be the bounds for your integral. The last video in the sequence, the next one after this, is about using the graphing calculator to do this, and the format of that video is going to be different, but it should be a good time. So hopefully you've got your TI-84 or compatible calculator, and you've got that ready to go to the next video. So I'll see you there.